Previously, we have covered section 4.5 on molarity and concentration. Today we'll be moving on and applying that information in section 4.6 on titrations. A titration is an analytical technique used to determine the concentration of a solution. Imagine that you have to determine the concentrations of ions in a sample of lake water, or that you have an unknown acid or base solution in which you wish to find the concentration. A titration would be the technique you would be used to accomplish these things. Two important terms when you perform a titration are equivalence point and end point. The equivalence point, if you look at the term, the first part of the word looks very similar to the word equal. And the equivalence point in a titration is when the number of moles of acid equal the number of moles of base. So you could say that the solution is neutral. The end point of a solution is the point just past equivalence point where the indicator changes color. For our purposes, when we do a titration, we will get to the equivalence point, the acid and the base will be neutral, and if there's an indicator present, like phenolphthalein, it would be colorless. Once you get to the end point and add just one additional drop of base, you will see a transition from colorless to pink. This slide summarizes some common acid-base indicators and the colors and ranges in which they work. Phenolphthalein, which I mentioned, you can see is colorless anywhere below around 8, pH of 8, and then transitions to a pink color in with the more basic solutions. Let's take a look at how a titration is performed. Now you have these steps on your handout, your notes handout, and this video will show you how to complete a titration.
Today we'll review some of the steps used to do a basic acid-base titration. Before you begin, some equipment you will need: a base solution and a funnel to use to fill the burette, a burette clamp and ring stand, an Erlenmeyer flask, an acid solution, and an indicator. Most oftentimes we will use phenolphthalein. Our first step is to place an aliquot of acid in the flask. An aliquot just means a set amount. Usually we use 10 or 15 milliliters. We'll use 15 in this example. Once you've added the acid to the flask, be sure to add an indicator. 1 drop is usually sufficient. We are using phenolphthalein, and 1 drop of phenolphthalein in an acid solution will not cause any color change. I like to place the flask on a white sheet of paper so that I can detect the color change more easily. We're now going to get our burette ready, or prepare the burette. One thing about using burettes is you can't assure that it's clean when you get to it, so an important step is to load the burette properly. And we do that by rinsing the burette with whatever solution is going to be used for titrating. You want to make sure that the stopcock is closed, meaning it's parallel to the floor. Always use a funnel. I'm going to add a little bit of the solution, in this case a base, so that I can rinse it out. A few inches or a few milliliters will do. And I run some of the solution out of the top of the burette and out of the bottom as well. Then I will fill the burette, or load the burette. It's also important when you're using a funnel never to pour above your head. Otherwise you might get some of that base solution in your eye, which wouldn't make for a good day. It's best to not have the funnel sitting directly on the top of the burette so that air can get into the burette so that it doesn't overflow. It's not necessary to fill it completely to the top. Somewhere near the top, however, is a good idea. One last thing before I can begin is to make sure I bleed the tip. I don't want any air bubbles messing with my data. I'm now ready to begin titrating. The first thing I should do before I begin, however, is to record my initial volume. Keep in mind that burettes, the numbers in a burette, the numbers get larger as you go down. So if it's between 4 and 5 milliliters, it will be 4 point something, not 5 point something. Because it's marked in tenths, you should be able to estimate the volume to the hundredths place. I'm going to record my initial volume as 4.3 milliliters. Since it's right on the line, I would add a 0. I'm now ready to begin titrating. When you titrate, you want to add just enough of the solution you're titrating with so that a slight color change persists. In this case, since I'm adding a base, you can see that the pink color appears when the drops hit the middle of the flask, but as soon as I swirl, they disappear. Beginning of the titration, you can add the base a little more quickly, but as the color starts persisting longer and longer, you should probably slow down. And instead of adding small squirts or amounts of base, switch to drop by drop. take your time. You want to add 1 drop to cause the color change to occur. Sometimes it will appear that the color change has taken place, but then it will fade again. I like to say that the color has to have staying power. It needs to last at least 30 seconds. And your goal is to get the color change to occur in 1 drop. Once the color change has stayed for at least 30 seconds, you can record your final volume and do your calculations.
Now that we've seen the steps that are used in a titration, we really need to make sure we understand how the calculations work. The steps are as follows. Start by writing a balanced neutralization equation. We talked about these last week. Acid plus base makes salt and water, or keep in mind all acid-base neutralization equations are really just double replacement reactions. Step 2. Find moles of your known. And a hint for you, if you start with volume, if you are given liters information or milliliters information, you should use molarity as a conversion factor. Once you have moles, as in any stoichiometry problem, our next step is to use the mole-to-mole ratio to find moles of unknown. Our last step is to use the molarity formula. Molarity is moles over liters, to solve for either molarity or liters. If they happen to ask for mass, of course, we can use molar mass like we have in the past with other stoichiometry type problems. At this point, you should turn to the stoichiometry diagram you have in your notebook. This was found back in section 3.6 when we introduced stoichiometry. As you can see from this slide, the information in the boxes on the slide should be all the information you have from section 3.6. At this point in the text, we had done stoichiometry including mass or grams and moles. But the bottom 2 boxes are still empty on your diagram, and here's our chance to complete those. In the bottom left box, you should put volume of A. And volume could be given either in milliliters or liters. The conversion factor to get from volume of A to moles of A is moles over liters, which is really just molarity. The bottom right box will either be molarity or volume of B. Remember, the whole point of a titration is to help you determine the concentration of an unknown solution, which would be molarity. But sometimes the question may be worded where they ask how many milliliters of this solution would be needed to reach the end point, in which case you would be solving for volume. The molarity formula is the one you should use for this conversion from moles to molarity or volume. If you're solving for molarity, you would just divide moles by liters, as it is shown in the equation. If you are solving for volume, however, you would rearrange the formula to solve for liters, which would be moles divided by molarity. Let's take a look at some examples. Before we begin, be sure you have your calculator and periodic table handy. Example 1. How many grams of calcium hydroxide are needed to neutralize 25 milliliters of 0.1 molar HNO3, nitric acid? We should start by writing a balanced neutralization equation. Acid plus base makes salt and water. My acid in this case is HNO3. And my base is calcium hydroxide. You can think of this as a double replacement reaction. The calcium and hydrogen will switch places, and so we get calcium nitrate, CaNO3 in parentheses, 2, and water, H2O. We do need to balance this before we can move on. And taking a look, we would need a coefficient of 2 in front of nitric acid and 2 in front of water. So we've completed our balanced neutralization equation. I think it is helpful in titration problems to take a moment and record the information we know below each substance. The nitric acid I know is 0.1 molar. And I also know that I have 25 milliliters of it. 25 milliliters is 0.025 liters. I also know that I have been asked to find how many grams of calcium hydroxide. By taking a moment to set up all your information, it makes a little clearer what to do with the math. Step 2 on your calculations say to find moles known. And it also says in your notes that if you start with volume, you can use molarity as a conversion factor. So I'm going to start with volume, 0.0250 liters HNO3. And really we need to get in the habit of using molarity as a conversion factor. Think of the capital M as moles per liter. So I'm going to write 0.100 moles per liter. And again, that's HNO3. Then we get to our mole-to-mole ratio. This is like stoichiometry, where our given information, the nitric acid, is really our A, our given, and calcium hydroxide is our B, or our unknown. And when we write our mole-to-mole ratio, it's always going to be B over A. So for every 1 mole of calcium hydroxide, there are 2 moles of HNO3. Keeping track of our units so far, the liters are gone, the moles of nitric acid are gone, and right now I have moles of calcium hydroxide. The last step on our stoich diagram, since we're at moles and it asks for mass or grams, I need to use the molar mass of calcium hydroxide. If you use your periodic table, you'll find the molar mass is 74.0946. And that is grams for every 1 mole. After crunching the numbers, you should come up with 0.0926 grams of calcium hydroxide. Please be sure that this calculation makes sense and everyone arrives at this answer before you move on. Let's take another look at a problem. Example 2. Fred the chemist is in the lab working on titrations. Looks like Fred is looking very sharp today. Fred starts by placing 25 milliliters of 0.15 molar phosphoric acid in a flask and titrates the acid with 0.250 molar NaOH. How many milliliters are required to reach the endpoint? We should start again by completing a balanced equation. The two things that are reacting are phosphoric acid and sodium hydroxide. Phosphoric acid is H3PO4 and sodium hydroxide is NaOH. This is another example of a neutralization equation or a double replacement reaction. The hydrogen and sodium will switch places, and so we will get sodium phosphate, and if you check the charges, sodium is +1 and phosphate is -3, so it should be written Na3PO4, and the other product is water. To balance, we'd need a coefficient of 3 in front of NaOH and a 3 in front of water. We should now list the information we know below each substance. The first number I see in the problem is 25 milliliters of phosphoric acid. 25 milliliters is 0.025 liters. So I'll list that below the H3PO4. We also know that is 0.15 molar. The sodium hydroxide has a concentration of 0.25. And we are asked to find how many milliliters of base are required to reach the endpoint. Thinking about this from a stoichiometry standpoint, we want to eventually get to moles. Moles can be found by taking molarity times liters. So by listing the information in this way, I have found that phosphoric acid is my A because I have both a molarity and a liters for that substance. So starting with the volume, 0.025, 0.15, nope, that was right, 0.025 liters. And then the molarity, remember, is a conversion factor, 0.150, but instead of writing it as M, we're going to write it as moles per liter, and I really should write the substance also, H3PO4. Liters will cancel out, and I'll get to moles. Then we need our mole-to-mole ratio. We are solving for sodium hydroxide, and there are 3 moles of sodium hydroxide for every 1 mole of phosphoric acid. If I perform that part of the calculation, I'll get 0.01125 moles of NaOH. I have been asked to find milliliters. Now remember, molarity is moles over liters. If I rearrange, liters is moles divided by molarity. I already have moles, so I need to divide by molarity. Now some students look at the problem and say, I have 2 molarity numbers, which one do I use? We've already used the 0.025 liters and the 0.15 molar. Those numbers have been used already. The other number, the 0.25 molar, is the one I should use. And another way to know that it's the correct number is that it is the molarity of the NaOH. and it's the NaOH that I'm trying to solve for. So I divide by 0.25 molar, and I get an answer of 0.045 liters. I'm almost done, but the problem does ask for milliliters. So I need to move my decimal 3 places to the right, and the answer would be 45.0 milliliters. Again, please ensure that everyone has come to this answer before we move on to the next problem. Example 3. Rather than an acid-base titration, this titration problem involves trying to figure out how much chloride is present in a water sample. It says the quantity of chloride ion in a water supply is determined by titrating the sample with silver +1 ions. The equation is as follows. Silver ions plus chloride ions yields silver chloride precipitate, or solid. The question is, how many grams of chloride ion are in a sample of the water if 20.2 mils of 0.1 molar silver ions are needed to react with all the chloride ion in the sample? This time the equation's been written for us, but I like to rewrite it just so that I can record the information I know below it. It says that we have 20.2 milliliters of silver ions. Changing that to liters, I'd move my decimal 3 places to the left, 0.0202 liters. And we know the concentration of the silver ions is 0.1. We would like to find how many grams of chloride are present. If you look at the information we've been provided, a molarity and a liters, and we're looking for grams. This is very similar to example 1 that we started with today. So at this point, I'd like you to pause the presentation, get into groups of 3 or 4, and work through the calculations. After everyone has had a chance to work on it, you may resume the video to see the correct answer. In keeping with the other 2 problems, we started with liters in both of those problems, so we will do the same here. 0.0202 liters of silver ions. And we use the molarity as a conversion factor. Remember, whenever you see mole, M, capital M, we should think moles per liter. So 0.100 moles per liter, and that is moles of silver ions. This time our ratio is 1 to 1. We're solving for chloride. So 1 mole of chloride ions for every 1 mole of silver ions. And at this point in your stoich diagram, we've gone from volume up to moles of A. We used our mole-to-mole ratio to get to moles of B. And the last thing we're asked to find is grams. So on the periodic table, if you look up the molar mass for chlorine, it's 35.453 grams for every 1 mole. Crunching out our answer, we should get 0.0716 grams of chloride ions present. Moving on to the next example. Before we start this example, please make sure everybody can make any corrections they need to on the previous example that they worked on. This example, I'd like you to think about McDonald's French fries as we work through this one. It says one commercial method used to peel potatoes is to soak them in a solution of NaOH for a short time, remove them from the NaOH, and spray off the peel. The concentration of NaOH is normally in the range of 3 molar to 6 molar. And this sodium hydroxide solution is analyzed periodically. And they would have to do this to ensure that it is in the proper concentration range. In one such analysis, 45.7 milliliters of 0.5 molar sulfuric acid is required to neutralize a 20 ml sample of NaOH solution. What is the concentration of the NaOH solution? So there's a lot of information here. This is an example of one of those typical college textbook problems where they give you all sorts of background information, and sometimes that makes the problem a little more cumbersome and a little bit more confusing. But we need to start in the same process that we've used previously, which is to start with a balanced equation. I know that the NaOH, which is used to peel the potatoes, has to be analyzed every once in a while, and to do so, they titrate it with sulfuric acid. So those are my two reactants, sodium hydroxide and sulfuric acid. Sulfuric acid is H2SO4, and it's reacting with NaOH. The products would be sodium sulfate, which if you do the crisscross, sodium is +1, sulfate is -2, so it's Na2SO4, and our other product is water. Taking a look at the coefficients, we can place a 2 in front of NaOH and a 2 in front of water. And I'm going to go back through the problem and read what I know. Now it says the concentration of NaOH is normally in the range of 3 to 6 molar. That we're going to need at the end of the problem to see if our NaOH solution is still good or not. If I keep reading in this analysis, in one such analysis, 45.7 mils of sulfuric acid. Changing that to liters, I would have 0.0457 liters. We also know that the concentration of the sulfuric acid is 0.5 molar. This much acid is required to neutralize 20 milliliters of NaOH. So I'm going to write 0.0200 liters. And I want to know what is the molarity. We would start by finding moles, and we always find moles by taking molarity times liters. So I'm going to start with my volume, 0.0457 liters of H2SO4. Molarity, remember to always think of as moles per liter, so 0.5 moles, and that is moles of H2SO4 per liter, cancels out my liters. I'm looking for sodium hydroxide, that is my B in terms of the stoichiometry. So the mole to mole ratio would be 2 moles of NaOH for every 1 mole of H2SO4. That allows us to cross out our moles of H2SO4. And at this point, we can find the number of moles. If you crunch out those numbers, everybody should be doing this along with me, don't be that student. 0.0457 moles of NaOH. And remember, molarity, moles per liter, so we divide by our liters of NaOH, 0.0200 liters, which gives me a concentration of 2.29 molar. So if you worked at a plant where they produced French fries and they had to peel these potatoes, and you were the chemist involved at that plant where you had to tell them if the NaOH was appropriate concentration or not, in this case you would say no, it needs to be replaced because it is not in the range of 3 to 6 molar. We have one problem to go, and before we do so, again, please make sure everyone is caught up on this one before we move on. This is our fifth and last example. This is a precipitation example of a titration. It says calculate the mass of solid NaCl that must be added to 1.5 liters of a 0.1 molar silver nitrate solution to precipitate all the silver ions in the form of AgCl. And again, this is one I would like you to try with your groups, but before we split into those groups, I will help you get a balanced equation to start with. So our two things that are reacting are sodium chloride. It's going to react with the silver nitrate in order to form AgCl. It's going to form a precipitate. So NaCl plus AgNO3 and this is a double replacement form of a precipitation reaction. So we will get silver chloride, that's my precipitate, and sodium nitrate. Because the ions are all +1 or -1, there are no coefficients necessary. Reading back through the problem, we know we are looking for grams of NaCl, that's my unknown or my B in this solution. Silver nitrate, I know that I have 1.5 liters of solution and that the concentration is 0.1. At this time, split into your groups, work through this problem, and once everybody's finished, you can take a look at the solution. Let's take a look and see how things went. Start with my volume, 1.50 liters. We use molarity as a conversion factor, 0.100 moles per liter, and that is moles of AgNO3. Our mole-to-mole ratio, B over A, is 1 mole of NaCl for every 1 mole of silver nitrate. And since I need to go to grams, I can keep going with my dimensional analysis. 1 mole of NaCl, if you used your periodic table and added up the atomic weights of sodium and chloride, you would get 58.44277 grams, which after all the number crunching comes out to be 8.77 grams.